So that last set or last week, what we looked at was the alkene, right? Technically the alkene and the alkyne, both of which are what we would define as non-polar pi bonds. So while they are both reactive largely because of the pi bond, and in the alkyne we've got two of them, that pi bond is non-polar. So there isn't really a preference on either carbon necessarily onto where the electrons move. Okay, we can see some kind of shifts come out of that if we change our substitution patterns. So if we were to change the substitution pattern and then look at resonance, we would expect the electrons to build primarily, call those hydrogens, on our less substituted carbon because that would form a more stable anion. Or we could conversely say that we would expect the electrons to go away from the more substituted position because the more substituted position would be a more stable carbocation. Okay? So all the reagents you end up looking at are how do we leverage and make that pi bond react. Right? In those processes, really all we were really kind of going through and doing is saying that the two ways that we could make it react is since it's an electron source, we could react it with acids or we could react it with electrophiles. One of the necessary repercussions that comes out of that is that once you've reacted one side of it, say we put on an extra hydrogen because we reacted it as an acid, that the other position, called those R groups, would be a carbocation, and that carbocation then needs to react in a secondary reaction. That secondary reaction is going to depend on what you're looking at, but it's usually some type of nucleophile, so an electron donor. And that was largely all we really talked about. After that, it's now what are the acids that you could react with, which is relatively limited. You're really just looking at your strong acids. And then the more challenging one, I would argue, is the electrophiles. It's what are the electrophiles that you could react it with. And that's where you get a whole bunch of different electrophiles, a whole bunch of different reagents, and that's where things can get really, really complex, really, 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 really fast. And the mechanisms behind those don't sit neatly, okay, within any particular patterns. They become very messy, and lots of information gets stored and stashed in those. Okay, and that's where we went back to, I'm going to regret doing it this way, but we're doing it this way anyway. That's where we go back to, oh my goodness, it's way back there. These spider diagrams, okay, which is summarizing all of the reactions that you are ultimately responsible for, okay? Which I do want to point out as another aspect. If we're looking at the final, your final is 70 questions. Some of it, a large portion of it is review. I think you're looking at 10 to 15 questions per unit, and then the remainder being unit 4. Okay, so even at its largest amount, you're looking at maybe 30 questions from this 4th unit. Okay, and I think that's a little on the high side. It's closer to 20. I can't ask a question about every single reaction. I just can't. So how you decide to divvy up your time is going to kind of be your choice, but that's kind of how all studying goes. As you're not going to see everything, you could push to the fundamentals, rely on the fundamentals, and then guess on the rest. So remember what we talked about with how many questions you need right to achieve certain grades. You could put Unit 4 into that category of I'm just going to get those questions wrong. Okay? And that's okay, but if you're going to do so, you do also need to remember the flags that allow you to say, this is a question I'm choosing to get wrong. You're looking for those nonpolar pi bonds and perhaps looking for really foreign reagents, chemicals that you're just like, I've never seen that before. Okay. And now I should just close out of this. But I've committed already to tapping. What we're moving to within this next week is what happens when we look at a polar pi bond. So the nonpolar pi bond, there was no difference in electronegativity, but now there is a difference in electronegativity. So if we just kind of consider where the electrons in this pi bond would go, we would predict them to shift up towards the oxygen, because oxygen is more electronegative than the carbon. This generates a large partial negative and a large partial positive. And I think I've color-coded this way before from that kind of scenario. If we push on this a little bit further, we can take this to a resonance system or a resonance structure, and we can go through and see that we can form a formal negative and a formal positive. Between these two structures, the one on the left is by far the best. We have no formal charges, right? But the one on the right helps us to see where the chemistry lies within this molecule, which then sets us up with the next question. Which is the active chemistry, the positive or the negative? Right? And it's a really challenging question. Okay? But I would argue, particularly hindsight being 2020, I know all the chemistry that's going to be coming up through this. The vast majority of the chemistry that we talk about when we look at carbonyl chemistry is the positive, not the negative. Okay? The negative is still accessible. It still has lots of chemistry associated with it, okay? But it is kind of secondary to the positive. Knowing that, why? Why might the positive be the more reactive site than the negative? Why is it more stable?
Because you need electron.
Okay, and that becomes kind of the important point here. If we think back to Unit 1, withdrawing Lewis structures, when we draw out our Lewis structures, the number one thing we have to satisfy is octets. And if we look, the oxygen has its octet. The carbon does not. Because the carbon is missing its octet, that's the primary focus of all of our chemical reactions. Okay? That doesn't mean the negative doesn't react. It absolutely still does, and we can still make it react first. Okay? But the primary chemistry that we're focused on is the carbon, which then sets us up with, well, what chemistry is it? How would we define the chemistry of that carbon? So we've already kind of addressed that it is a polar covalent bond. The resonance behind that polarity helps us to see that that carbon is positive. Okay? But when we talk through chemistry, we tend to not say, well, it's a positive carbon, this is how it reacts. We give it a name. What is that name that we give positive atoms? You're not wrong. That's what I was fishing for. Okay? So when we talk through the chemistry through this class, there were 4 categories that we talked through: acid, base, electrophile, nucleophile. That's it. Which means when you go through to look at a structure and you're trying to figure out its chemistry, you should be classifying it according to those things. Because once you have it classified according to those things, you can now start to predict how it's going to react. Calling it a carbocation isn't necessarily bad because it is a carbocation. Cation is a little bit more generic, and even calling it a cation helps to give you some information, because how should it react? It needs to react with electrons. Absolutely fair game. The language that we choose to use within chemistry is referencing it as an electrophile. So that becomes the primary chemistry, and if you move through into biochemistry and you look at carbonyls, they show up everywhere. Okay, so they're in almost all of our biological systems, and they almost all universally react through that electrophilic carbon site. Okay, which means if we're going to think about what they react with, we need to look for nucleophiles. Well, how do we know we have a nucleophile? What is characteristic of a nucleophile? So we could look for negative charge. Okay, early on in the semester, that's what we looked for. We looked for absolute positives and negatives. But very quickly we noted that those positives and negatives became partial and they became hidden. Okay? So more generically for our for our nucleophile, it needs to be a source of electrons, which is a negative. Negatives are sources of electrons. Okay, but it just needs to be a source of electrons, which is usually lone pairs. Are we going to see negatives? Yeah, negatives are lone pairs as well, but it's now in excess of those electrons at that spot. Okay? And really the difference between just lone pairs and a negative is the strength. If we see a negative, we might call this a strong nucleophile. If we just saw lone pairs, we could call it a weak nucleophile. That was the point of our last unit, okay? Teasing and pushing at those kind of definitions. Okay. Could we call the carbon an acid?
Yes.
If we called it an acid, what would it react with?
Hydrogens.
It would react with a base. Okay. How do bases react? So there's two terms that go with our definition. So depending on what you follow except with, you could be right or wrong. So bases accept H plus. Okay. So how do bases accept H plus?
Electrons, lone pairs, they didn't make a bond.
They donate electrons. So if we had the base there, we would have to add those electrons. And if it shared those electrons with the carbon, did I do an acid-base reaction? You've now shared electrons between base and carbon, which means we've now formed a bond between base and carbon. Did it accept a hydrogen? Is carbon hydrogen? Is base hydrogen? No. Did it act as an acid? No. Okay. So the carbon cannot act as an acid because it's not a hydrogen. Acids, by definition, are hydrogen donors. That carbon is not a positive hydrogen, so it cannot act. We're going to change that question in a little bit, so I'm going to leave the base up there for a second. Okay, because what we're going to look at is the secondary kind of chemistry of our carbonyls. I guess I would call it tertiary. So our primary chemistry would be the electrophilic carbon. Okay, it can't act as an acid, so we're stuck with it just being an electrophile. What happens with the oxygen? Because that's now also negatively charged. How could the oxygen react? To act as a leaving group, we would have to be referencing this sigma bond and saying that oxygen can take the electrons away from that carbon. As a leaving group, it would then be a -2 charge. If we think to leaving group abilities, what we'd be navigating to very first right out of the gate is charge, and we want to minimize the charge as much as possible. Is a -2 minimizing the charge? No. So leaving group is not a good option. We'll say it again. There are 4 primary chemistries. You need to know those 4 primary chemistries. Right? Why do you think it could act as a nucleophile?
Because
And what do nucleophiles do? Yeah, they donate electrons. So it has extra electrons, so we could look at that as the potential to act as a nucleophile. You'll note that where I drew it was lower than the 2. Because that's actually the secondary chemistry of this, or the secondary chemistry of our oxygen. That oxygen's electrons are already kind of preoccupied within the carbon. For it to act as a nucleophile, it needs to form technically a third bond to another atom. That's now distributing oxygen's electrons over a very large area. Is oxygen okay spreading its electrons over a very large area? Why not? A hint would be number 2. Sounds a little weird, but. Or second. Base is absolutely a better role for it. Oxygen is the second most electronegative element. Okay? It does not want to share its electrons around. And if it's acting as a nucleophile, it's sharing it with something that is relatively higher in electronegativity than hydrogen, because hydrogen is effectively our bottom. Okay? So if it acts as a base, it shares the electrons with the hydrogen being low in electronegativity. That ain't great. It's still spreading across multiple atoms for those electrons, but it's sharing them with an atom that's relatively low in electronegativity. If we look at the nucleophile characteristics are by definition going to share with something other than hydrogen, which means the electronegativity by definition will be higher than it will be for hydrogen. Oxygen's going to not like that as much. So the nucleophile chemistry will play usually second fiddle to the base chemistry when we're looking at the carbonyl oxygen. It can still act as a nucleophile, okay, but it's relatively limited and you're looking at special cases. One of the things that we haven't really addressed this semester is a lot of chemical reactions get names associated with them, and it's the name of the person that discovered them. If we go through and look at the chemistry of our carbonyls, it acting as an electrophile in and of itself, not a big deal. No name is directly associated with that. No name is associated with the oxygen acting as a base. Names are associated with the oxygen of a carbonyl acting as a nucleophile. So whoever forced the oxygen to do that gets to attach their name to the chemical reaction. Okay? So typically, names are associated with things that are very, very challenging to go through and do. They shouldn't be associated with really easy chemistries. Okay? So what we've covered here are 3 chemistries. I would argue one very much primary. The base chemistry is relatively minor because acid-base chemistry is just the transfer of a hydrogen. Transfer of hydrogens are very reversible. They can come on and off of a structure almost at will. Okay? So that base chemistry of our oxygen is largely just catalytic. Okay? And what it's being used to do is to activate the electrophile. That's it. The oxygen acting as a nucleophile, for the sake of this class, I don't think we talk about it at all. It's non-existent. It is there, we just don't address it for this class. Right? Which then sets us up, well, we've now covered all the chemistry of our carbonyls. What are they going to react with? They're largely going to react with nucleophiles, and funnily enough, they will react with acids. Okay? The nucleophile is going to react with our electrophilic carbon, and acids will react with our basic oxygens. That acid-base reaction is largely in action to make the nucleophile reaction happen. That's it. Okay? Those are the primary chemistries of your carbonyl compound. If we take a step out and instead of looking at just the functional group or just the pi bond and now say what's connected to it, we make things slightly more complicated. If I put another carbon here and say a hydrogen, it turns out that that hydrogen is acidic. Why would that hydrogen be acidic? Why is any hydrogen acidic? Why does HCl produce H+?
Because the chlorine is going to take those electrons and go off by itself, leaving the hydrogen.
The chloride is exceptionally stable on its own, so it is absolutely willing to steal the electrons away from the hydrogen. What makes the chloride stable on its own?
It's large.
It's large. Okay. So when we're looking at ranking acidity, we're looking at the ability of the atom that's connected to our acidic hydrogen, its ability to stabilize the electrons. And we typically don't look at carbon-hydrogen bonds. Why do we not look at carbon-hydrogen bonds?
They're not acidic.
Why not?
They're non-polar bond.
So there's one part that you didn't address with the HCl. Chloride is also very electronegative.
And carbon and hydrogen aren't very electronegative.
So there's very little polarity associated with that. So that minimizes some of the chemistry. What else? What was your reason for explaining HCl was acidic?
They're both similar in terms of, like, they're not very electronegative, so neither of them are going to pull away.
That's not your explanation for HCl. What was your explanation for HCl being acidic?
That they're not very large.
Chloride was very, very large. Is carbon?
No.
No. Carbon is both small, low electronegativity, right? Doesn't stabilize the negative charge well.
No.
Okay? Which is why we never addressed it as being acidic. And yet, when we now move up to the structure above, I'm now saying it's acidic. Why would it now be acidic? I'm still forming that negative carbon. Isn't that bad? That's when you say, yes, that's bad. We shouldn't do that. And when we look at charge, the charge is bad. Size, it's carbon. Carbon can't stabilize the charge well, okay, based off of size, nor electronegativity. But is that all we look at when we evaluate stability? No, cool. That's a good start. What else do we look at? What's the next thing in the list? Resonance. Do I have resonance? I do indeed. That resonance is what allows that carbon to be acidic. And we now look at the overall product. We're not looking at a negative carbon, we're looking at a negative oxygen. Oxygen, being electronegative, can stabilize the charge. It turns out that the hydrogen right next to a carbonyl has about the same acidity as water. It's a little bit more acidic than water, actually. Okay. Water in itself isn't a great acid, but it's absolutely acidic. Okay. Why does that become powerful to us? Well, that makes a negative carbon. Negative carbons are insanely rare because negative carbons can't stabilize the charge well. Because they can't stabilize the charge well, we can't build larger structures. If I can't have negative carbons, I can't make larger and larger structures. Okay? This should universally be a problem for us. Okay? And yet something has figured out how to do it for us. What are we made out of? What's that?
Water.
Yeah, there's a lot of water in us.
Carbon.
And carbon. Okay? And a large part of our structure is a whole bunch of sequences of carbon bonds. The only way we can get those carbon bonds is either immaculate creation, right? And even then, maybe that gets you the baby. How does that get from baby to now? You all are significantly larger than you were as babies. You had to create more carbon-carbon bonds. The only way you can do that is by making negative carbons. What has biology figured out? That hydrogen is acidic. And in a biological system, we can remove that hydrogen and create a nucleophilic carbon. That carbon can then go through and do a whole bunch of secondary chemistry. That's pretty wicked. All right? So the carbonyl functional group has some core chemistry associated with it initially, and then it's got this secondary chemistry. That secondary chemistry, as far as y'all are concerned, is probably the more important chemistry, because that's the one that drives almost all of our biochemical reactions. Okay. How important is it? It does get a name. What we're referring to is a ketone over here. We usually drop the Ne. And over here, what we have is a special structure. It has an alkene, and it has the fundamentals of an alcohol. Because it's a negative alcohol, we can call it an olate, and we get the keto enolate tautomerization. That tautomerization is critical to almost all of biochem. In almost every single system that you go through and see, enzymes, probably even DNA editing, you're dealing with keto-enol tautomerizations. Okay, they're very, 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 very important. They show up a little bit less in our overarching chemistry, but they are there. So in kind of a grand summary, what we look at, okay, kind of initially, is just the carbonyl chemistry. So we look at it reacting as an electrophile with strong nucleophiles. We can get hydride nucleophiles. We can get carbon nucleophiles in the form of a specially named reagent called Grignards. Okay? Acetylides, we saw that on the last exam. Okay? And then you've got weak nucleophiles, your oxygen, nitrogen, and carbon, your enolates. To a much lesser extent do we actually talk about those. Okay? We set those up so that you have the ability to deal with those in biochem. Okay? How much do you need to stress about it for biochem? More than likely in biochem, they're going to say this is how this thing works. You don't have to know how it works in every scenario. You need to know how it works in that one scenario, because that's how biology works. Vitamins work in one space. They don't work in 30 spaces. It's a bit of an oversimplification, but close enough. All right. So the rest of this is all of the summary again. So just like our alkenes, you get a big summary of all the reagents. Note we get some core fundamental chemistry happening in the middle. This is the acknowledgement that we have that resonance ability. And how does that drive our chemistry? So if we look at our changes, we go to the left, what happened? We took that center carbon and we added the triple bond. Why? Because the triple bond had that negative carbon. Okay. When we go up, what happened? What did we change? There's an implied hydrogen there. Where did that hydrogen come from? Sodium borohydride. Okay. So that chemistry is all specified and hidden within this. You have to be careful to process and go through it. Just like we started out with the alkenes, you're looking at maybe 20 to 30 questions on this content. There's no way I can ask a question about every single reaction. Pick and choose to your preference and accept the ones that you don't know. Okay? Or freaking rock star it and spend all your time on it. That's also fair. Okay? I don't recommend that, but that's fine. Kind of, sort of. Okay? It gets worse because then we also see the weak nucleophiles. Okay? These were all the strong nucleophiles. These are now weak, or bringing in oxygens, nitrogens, and some other carbons. Okay? So all sorts of new reactions that get sistered in with all of those. Okay? Same process. We've got the core fundamental chemistry being addressed up at the top, and you're now branching out in each of those cases to acknowledge what's happening in each of those pieces. Kind of, sort of? Okay. After that, it's now all the plate posits. There's one that does a general kind of mechanism for your nucleophile addition. Officially, we just kind of address that. Once you know the core fundamental chemistry, you just repeat. Rinse and repeat. What's the new nucleophile? Rinse and repeat. Rinse and repeat. Okay, so it goes through, covers the core mechanism with all the core arrows, and then it goes through and talks about some weak nucleophiles, which is a bit painful because the weak nucleophiles bring in equilibrium, and unfortunately none of you know anything about equilibrium because that probably wasn't taught to any appropriate level within Chem 130. Ultimately, what is equilibrium? Reactions can go forwards and they can go backwards. All of biochem does this. Okay? So this goes through the detailed mechanisms, both hand-drawn and drawn out in detail. And what it's really going to push on is the formation of this special molecule known as the acetal. And actually, I'm not going to stop it here because I think I got there. That's what I wanted. This slide summarizes it all. I would argue right here on the far right is your big critical piece. You're starting with the carbonyl. That carbonyl reacts with electrons from an alcohol as a nucleophile, comes in and attacks. We've got our new bond to our OR. A second equivalent, which was not shown here, eventually comes in as well and kicks that out. The detail of the mechanism is all shown on the left, so you can follow all of those curved arrows to see what's going on within it. But ultimately what happens is you end with this new structure down here that's known as an acetal. Acetals in organic chemistry have very limited usage. Right? Typically what they're used for is what's known as a protecting group. So if we were going to try and make something, that something probably has lots of chemistry associated within that structure. If I only want one part of it to react, I have to make sure that none of the other parts can react. That can get really tricky, and that's where synthetic chemists create these things known as protecting groups. The protecting groups come in, change the functionality of those secondary groups, so that they're no longer that secondary group, but they're reversible and they can revert back. So if we were looking at a structure that had a carbonyl in it and I didn't want the carbonyl to react, I could convert the carbonyl to an acetal. I've lost that polar pi bond. I do whatever chemistry I want with other pi bonds, and then I reverse that process back to the carbonyl. Synthetically speaking, it's a generally frowned upon, particularly in modern society, because you're now adding extra steps that don't take you forwards. Okay? Education has the same issue. You go, oh, there's prerequisites. Okay? It says I only need biochemistry to get into pharmacy school. Okay? But what they aren't telling you is you also have to take general chemistry and organic chemistry to get to biochemistry. Okay? Those are kind of prerequisite steps behind it, and they're hiding that within the pharm school process. Okay? Which is a bit disingenuous, but it happens. Okay? You need to have that prerequisite knowledge. Here, the bigger issue is not just that kind of prerequisite system behind it, but what you're creating is a whole bunch more chemicals and a whole bunch of extra steps. We want to limit chemical exposure, not maximize it. And so protecting groups are kind of disappearing from the field a little bit because it's adding steps that don't advance you closer to your target. Okay? That increases risk for anybody working with it, and it increases waste, which astronomically increases costs for an individual chemical reaction. Why do we care about acetals in the sake of this class? Because we aren't concerned about synthesis, so why should we care about all of that? Well, what are we looking at here? So this is now new content. What do you see?
Glucose
Glucose. And where's glucose found?
in your body.
Yeah, we're looking at hardcore biochemical systems now. Okay, and in particular, when we're looking at glucose, what we're looking at is carbohydrates, and we're looking at the carbohydrate structure. Glucose can take on varying forms, okay, and you'll note that we'll also get some different nomenclature systems, because this isn't just glucose, this is beta D-glucose, and this one over here is alpha D-glucose. Well, the D's are the same, so let's ignore that for the moment. Why is one alpha and one beta? What's the difference?
It's the way it was the way they were found.
It's not the order in which they were found. I've done a little bit of digging on that. The claim is that they were found at the same time. I'm still not convinced about that. But what's the difference between those two structures?
Alpha is higher energy.
Okay, so we could look at energy. We can't actually look at energy very cleanly within these images. Okay, but if we switched them to chair conformers, we could see there's a significant energy difference between them, or a subtle energy difference that translates into a significant application difference. So you're right, there is an energy difference, and alpha is the higher one, but that's only because I've got that memorized. Are you staring at that saying, oh, alpha is clearly higher in energy, or did you do a good job memorizing it? Yeah, just fine. How is alpha different than beta?
Their arrangements are a little bit different.
I'm going to say no just because of how you said that. The arrangements, plural, are not different.
One arrangement.
Yes, only one arrangement is different. And if we look really, really carefully, it's at this carbon. Okay? That one carbon has a very subtle difference. We're either looking at the OH being aimed up or the OH being aimed down in the Hayworth projection. So if we remember back to this, okay? If we look at the middle structure, it just says D-glucose. Why does it not say alpha or beta? It's a really hard question. Because there is no alpha or beta. So what's the difference between the just D-glucose versus the alpha and beta forms?
It's just two versions of that same one.
I don't know what that means.
This is D-glucose, and then this is just with that one flip, and then this is like it's just I don't know.
But why is the middle one not being labeled as alpha or beta?
That's what your generic.
No. So push more simply, what is the difference between that middle structure and the two structures on the sides? Say again. It's a chain. And actually, Annie, what did you notice? There's a pi bond. In the middle one, I have a pi bond. What kind of pi bond do I have? I have a pi bond between an oxygen and a carbon. You mean I have a polar pi bond? Okay, it is an aldehyde functional group. Yeah, that polar pi bond, that aldehyde functional group, okay, we don't see in the two products. Okay, it has disappeared. Why did it disappear? Because what we went through and did was took, yeah, I just got to make sure I count right. We took that oxygen. That oxygen's kind of special, right? Why is that oxygen special? In fact, all oxygens are special. What do oxygens have on them? Lone pairs. And what is special about lone pairs? What can they do?
Bond.
Yes, they can be used as to make bonds. They can be used to act as nucleophiles. And what was special about our polar pi bond? What was its chemistry? It was an electrophile. And if I have an alcohol that can act as a nucleophile, and I have a polar pi bond that can act as an electrophile, what can I do? I can take these electrons and I can swing them up to react with that carbon. And now the fun part, a little bit of review. What is it reacting with on that carbon?
The electrons in the bond.
It can't be the electrons, because if the oxygen is donating electrons and there's electrons already up there, what are the electrons going to do?
Oh, push away.
They're going to repel and no chemical reaction happens.
The charge.
Well, what's the charge? Okay, so we can make some subtle adjustments to our aldehyde up here. Number one, I'm going to rotate it so it looks a little cleaner. Oops. There's our oxygen, there's our hydrogen. We've got a negative charge on the oxygen and we have a positive charge on the carbon. That positive charge is what can react with our oxygen. But again, I'm going to ask, where is that positive charge? Well, I'm going to change the question a little bit. Where is that positive charge? Don't tell me on the carbon, it's on the carbon.
It's like is it partial?
No, right now what we did is we broke that pi bond. It is formally positive right now. In our drawing, it is absolutely formally positive. That's kind of a hard question. So what we can do is take a step back and do some Unit 1 review. Unit 1 review, what is the hybridization of that carbon? sp2. Where are the sp2 orbitals aimed on that carbon? And we'll color them in blue. Where are the sp2 orbitals aimed on that carbon? What are the sp2 orbitals being used for?
To connect.
Give me a little more than that.
So it's would it be like one is kind of going this way, like up and down, and then the other orbital would be going this way?
Okay, so let's push on this a little bit. How many sp2 orbitals are there? There's 3. How do we know there's 3? There's 1 for S and there's 2 for the P. So there are 3 sp2 orbitals. What shape is generated from 3 sp2 orbitals? So there's an sp2 orbital, there's an sp2 orbital, there's an sp2 orbital. Trigonal planar. So again, back to our structure, where are the sp2 orbitals in our structure? Whoop. Go ahead, Sydney.
They're like the V at the top.
I'm just going to color it in. You mean the bond between the carbon and the oxygen?
Yes.
The bond between the carbon and the hydrogen?
Yes.
And you mean the bond between the carbon and the carbon? Okay. That's where our sp2 orbitals are. Where's the carbocation?
In between the V.
Is it in between the V there, or is it in between the V over here? Or is it in between the V over here? Does that suggest that maybe that's a problem to call it in between? Yes.
Well, I meant like in between the V at the top.
So it isn't orbital. Well, so that's what I'm saying. Why is it the V at the top? Why is it not the V to the side, one side or the other side?
Because it's the charge, so it's not gonna be, it's positive,
Good.
and that's gonna be your electron orbitals.
So
it's
there's a
gonna
good
be outside
reference.
out of it.
The carbocation has to be an orbital. What orbital?
Like S versus P, you mean? Or,
What orbital? Because you can say S versus P. You could also say sp2. You could say sp3. You could say sp. We have all of those as potential orbitals.
it would be in the S orbital.
Okay. What does it mean to be sp2? What did you do to make sp2 hybridized orbitals? sp2 hybridized orbitals is because you took the s orbital and two p orbitals. You smashed them together to make three new sp2 hybrid orbitals, which means do you have an s orbital anymore?
Don't you always have what's below? Oh.
It is consumed in the process of making the hybrid orbital. So you no longer have an s orbital. So you can't tell me the carbocation's in an s orbital because it's already being used in the sp2. What isn't being used to make an sp2 hybrid orbital? Where did the sp2 come from? Let's try that. We've already addressed part of it. The s orbital, the sp2 involved the s orbital. Where did the s orbital come from?
The hydrogen?
No. We were looking at the hybridization for our center carbon. And if we're looking at that center carbon, what are the orbitals the carbon atom brings to the party?
The S and
The s and the what?
the P.
How many s?
I don't know, one S, because you only have sp2, so it has one S. And
Why does it only have one s?
orbitals.
So this now goes all the way back to atomic structure back in Gen Chem.
That was a really long time ago.
Yeah, but we also covered it this semester. Right?
I don't know.
So if you're getting overwhelmed with new content, this new content is falling back heavily on old content. So one of the things that you may decide to do is that you need to go back and review the old content to ensure you know what's going on. When we look at our individual atoms, atoms come in with their atomic orbitals. Once we start to make bonds, we no longer have atomic orbitals, we have molecular orbitals. Okay? And our first approximation system that we've used as we shift from atomic to molecular is we do what's called hybridization. And we take our atomic orbitals and we hybridize them. But we only hybridize the highest energy orbitals. What are the highest energy orbitals for carbon?
P.
P is a high energy for carbon. It is not the only one. So let's try a different way. Carbon is the sixth element on the periodic table, which means if I look at a neutral carbon, how many electrons does it have? Yep, 6 electrons. I want you to tell me where all 6 electrons are located. Atomic orbitals.
To mass and falling feet.
No. If I look at hydrogen, hydrogen is the first element. It has only 1 electron. that 1 electron for hydrogen is located in the first energy level, because it's in the very first row of our periodic table. And since it's in the very first 2 columns, that's part of the S block. There's only 1 electron located in it, so I would call hydrogen 1s1. What would I call helium? Being the second element. It has 2 electrons. I would call it 1s1. That's where the first electron is. The second electron is located also in the first energy level, also still in that first block, 1s1, 1s1. Is that redundant? I wonder if I could simplify that. What could I simplify that to? Do it, yeah. The 1 is the energy level. If you now all of a sudden make that 2, you're now saying you're in the second row. We're still the first row. 1s2.
2p2.
We now have the electron configuration for carbon. And if we're going to look at how carbon bonds, what we're going to look at is the highest energy electrons. What part of our system, the 1, the S, or the superscript, were the energy level? The 1. So what are the highest energy orbitals for carbon? 2s2 and 2p2. How many p orbitals are there? So if we now build out our structure, we would have our 1s orbital. We go higher in energy, we have our 2s orbital, and then we'd have our 2p. How many 2p lines should I be drawing to represent the 2p orbitals? There were 3. The trick we could use for that is that there's 3 orientations of a dumbbell on our x, y, and then the unfortunate one that we can't draw very well on our z axis. We have 3 p orbitals. This becomes powerful because when we consider the bonding patterns that we look at for carbon, how many bonds can it maximally have? 4. And if I'm going to have 4 bonds, I need 4 orbitals. How many orbitals do I have at the highest energy level? Magically, I have 4. And if I want to explain how carbon can make 4 bonds, what I'm going through and doing is I'm taking that carbon and I'm taking all of those atomic orbitals and I'm mashing them all up to make 4 new orbitals. Each of those orbitals I would call sp3. And that would get me a tetrahedron. To make an sp2, what have I done? To get the sp3, how many p orbitals did I use? To make an sp3, how many p orbitals did I use? 3. Can I make an sp4? No, why not? I've never heard of it, Mike. That's fair. But why? Why not? Why not an sp6?
Because you move up to the next orbital.
How many p orbitals do I have? 3. Why do I not have sp4? There's no 4th p orbital. It doesn't exist. I can only go up to sp3. So if I'm going to go through and make this hybrid system, what do I have? I've got sp2, sp2, sp2. And if I'm going to talk about how carbon makes its bonds, I'm going to take those 4 electrons and I'm going to distribute them across the molecular orbitals. So I could say, oh, there's an electron, there's an electron, there's an electron. And then the other atom that's connected out there could now drop in an electron, electron, electron. But now I've got a problem. What happens with that last electron? Where would I place it? Because there's 4. Where do I have to place that 4th electron? I have to place it in an orbital. What orbital do I place it in? The 1s we ignored. The 2s we used to make our sp2s. I used 1/3 of it in each of those orbitals. How many p orbitals did I use?
3.
What was the name of the orbital? Most clearly written on this last one. What was the name of this orbital? sp2. When we said sp3, how many p orbitals did we use? 3. How many p orbitals did I use? For sp2. I used 2. So 2 of those are consumed. Can I destroy matter? Nope. What's left over? Yeah, what orbital? A p orbital. So if I were to look at a carbon that brought in all of its electrons, we could now put that 4th electron in that orbital. There we go. That would be lovely. Go back up to the carbon that we're talking about. What charge is that carbon? Positively charged. To become positively charged, what did we have to do?
Lost electron.
We had to lose an electron. What electron would we have lost?
The 1. Just the 1 in it.
Why?
Because it's not completely filled like the other ones are.
I'll accept that. So due to symmetry reasons, there's another reason. So I don't like the word weaker, but I think you're getting at the right idea. The p orbital is higher in energy. It's higher in energy. That's the easiest electron to get rid of. Where's the carbocation? It's sitting in a place that has no electrons. What is that place?
The extra p orbital.
A p orbital. Where's the p orbital on that carbon? Shape. Is coming in and out of the plane at you. So there's a p orbital lobe hanging out in front of the plane. There's also a p orbital lobe hanging out behind the plane of this board. So that oxygen, when it shares electrons, where could it place the electrons?
In that orbital.
Which part of that orbital?
What do you mean, which part?
Because that orbital had 2 empty spaces. A p orbital has a lobe both on top and on bottom, in front of the plane and behind it. So where could it place the electron? So here's the p orbital. There's the one coming out at you. There's the one going away. I could have placed the electrons from that oxygen into that top part, or I could go into the bottom part. Both of those are options. Why does that matter?
Does it matter where your negative is? That's gonna push it away.
Sort of. That's the end result. If we have that oxygen come through and attack from the top side, the bond between that oxygen and that carbon should be up, wedged, which would mean, where's that oxygen?
It's just
Away. You mean it's aimed down? What if it had come in and attacked from the bottom side?
it would push it
It would push the oxygen.
up.
The difference between beta and alpha glucose is just how you formed the ring. how you overlap the electrons on this oxygen with that p orbital. That's it. An insanely subtle change that drastically changes the output of the glucose. Why does it do it that way? Well, if we look at a slightly different form, there's for sure a better image of this, and if you go all the way back to the model lecture, because we can take this Fisher projection, and eventually what you can see is that it cyclizes kind of around like this. It forms a corkscrew. And if that corkscrew overlaps where this is on top, we get one result. If the corkscrew forms where that's on the bottom, you get different results. But what you're talking about is how that corkscrew spins, which direction it spins. What you're talking about is chirality. Okay? The handedness of the spin. Why does that matter? Everything in biology has a hand. There's always a handedness associated with it. So depending on what the particular enzyme is that's trying to process D-glucose, if that enzyme is trying to process D-glucose so that it can make energy storage, it's going to spin it so that we get alpha D-glucose. If that enzyme is trying to make a structure or something to build a larger compound with, like cell walls, it spins it the other direction so that you get beta. And you're looking at an insanely subtle difference in which way you corkscrew. That's it. And you change from energy, I can process things, to I can't touch this. This is why we as humans have a hard time eating trees. They have tons of glucose in them. There's tons of energy stored in there, but it's stored with a different spin. Our bodies can't process that spin. Okay? Because we didn't build enzymes to do that. Or potentially, evolutionarily, plants recognized a defense mechanism that animals won't eat me if I spin the other direction because they don't have the stuff to process it. And they will instead go after other things. That's pretty wicked. Right? And what that is looking at is the reaction of a nucleophile with a polar pi bond. And in particular, a weak nucleophile oxygen reacting with that polar pi bond, which produces at that red carbon an acetal of varying forms. Officially, this one isn't an acetal. Okay? And depending on which direction that oxygen is aimed, that changes the alpha or beta statement. And so you as a biochemist, okay, or a nutritionist would have to know which one you're looking at. Because one form is biologically useful and the other form is biologically useless for us. That's a pretty neat difference. An extra thing that I honestly don't know anything about, if you took beta glucose versus alpha glucose and you put them into your food, do they taste the same? I don't think so. I think when we taste sweet, we are only tasting alpha glucose. We're not tasting beta glucose. It'd be neat if they did both taste sweet, right? And you could just eat beta glucose. It would taste sweet and lovely, but you would never be able to process it. It'd probably give you stomach problems because it would just right out your system. But, that could be kind of cool. Okay. What's the D part of? We didn't talk about optical activity, but optical activity is when you take, say, molecules like glucose and you shine light at them. When you shine light at them, particularly plain polarized light, it rotates light. So if you've ever taken, has anybody tried this, taken polarized sunglasses? If you take two pairs of polarized sunglasses and you turn them 90 degrees to each other, what you will find is no light passes through anymore. Okay? So you can line them up, same alignment, light will pass through. It'll be darker because you're passing through two shades, but you turn them 90 degrees, no light should pass through. It's a good test to know if you actually have polarized sunglasses or not. Okay? Because what happens with those polarized glasses is they're removing half of the visible light. They're saying all light coming in on the horizontal axis does not make it through the lens. All light on the vertical axis is fine, which is why when you turn two pairs and line them up, you've changed the orientation of those, which is why light doesn't pass through anymore. Okay? But it turns out biological systems, when you take a sample of them and shine this polarized light at them, they will rotate light. It is a way for us to experimentally see that chirality is a thing. Okay? Lots of different systems came about with this. Depending on which direction the light rotates, you could hear reference to L versus D, or negative and positive, and what those are talking about is how it's rotated the light. Did it rotate it to the left, it's L. If you rotate it to the right, it's D. D is dextrorotatory. Okay? And if you look at a 0 point being vertical, if it rotates to the right, it's the positive direction. If it rotates to the left, it's the negative direction. Okay? But if we look here, this is a capital D, not a lowercase d. Does that mean it's something else? Yeah, it does. You can hear reference to L and D glucoses. I think you can also hear it referenced to amino. I think you can hear it referenced to amino acids, but that might be looking at these ones. I'm not positive. When you're looking at that L and the capital L and D, we are talking about chirality. If we look at glucose, how many chiral centers are there? 1, 2, 3, 4. There's 4 chiral atoms. So you could go through and assign R and S to each one of those. Fisher got really sick and tired of doing that because Fisher studied carbohydrates. In organic chemistry, when we go through and deal with R's and S's, we're looking at 1 or 2, not a big deal. You look at glucose, you got 4. I don't want to deal with all of that. So what did he go through and do is he created a naming system that would hopefully simplify it all. It didn't simplify it at all, but it stuck. Okay? Take a look at the penultimate carbon. So this is carbon 1, 2, 3, 4, 5, 6. Penultimate means second to last. This guy. Look where the OH is. Is it on the right-hand side or the left-hand side? It's on the right-hand side of the structure. And what did we say right represented? D. That's where the capital D comes from. So if you look at L-glucose, the only difference is the OH is over here. The rest of this structure is the same. Okay? It's an interesting nomenclature system. I don't think I like it or agree with it, but I will accept that it's an interesting naming system. Okay? So, why worry about carbonyl chemistry? Acetals. Okay? And acetals are important because of carbohydrates. Okay? That special carbon, okay, where we have that acetal-like system happening, is often referred to as the anomeric carbon. I don't have a cute story on that one. That's all I know. It's referenced as the anomeric carbon. So depending on which way that OH is aimed or that oxygen is aimed, you have the different anomeric forms, alpha versus beta. Does it have to be OH? No. This could connect immediately to another carbohydrate. I drew that horrendously wrong. I'm not making it any better. Oh my God. You guys know how to draw carbohydrates better than me. Okay. So it does not have to be an H. It can be another carbon structure. And because I drew that so horribly, I'm going to actually find a better one. So we'll open this up real quickly. I think. Yeah, good. So if you look at a structure for sucrose, let's look at that. Sucrose is taking 2 carbohydrates, glucose and fructose, and it's connecting them. Okay? Where do we have anomeric carbons? Well, you've got the anomeric carbon on glucose right there. Where's the anomeric carbon on fructose? What made it anomeric? It's the carbon where you have two oxygens connected. Is that anomeric? Actually, it technically is. I didn't actually see that. Is this anomeric? Sorry, that color didn't work out very well. Let's try blue. That one's also an anomeric carbon. Okay. There is some kind of weird oddities here. Note there's a bend there. And what did we say points were? Carbons. Is that a carbon? No. Why? I don't know. Talk to a biologist. Or a biochemist to explain that one. Okay, I think it's an artifact of how they draw things. They just decided it looked prettier if they made a bend there. But that's not a carbon. That's the continuation of the carbon-oxygen bond. Okay? So you can hear reference to identifying anomeric carbons in biochem. You can also sometimes, depending on it, why is that showing up as sucrose? Is that a name of a character?
I don't know, I was thinking that too, that's weird.
I mean, it's gotta be. Jiminy Christmas, look at all those. Kind of the last thing on that. Way back when I showed you the aldose family tree when we looked at things. These are all our carbohydrates. CHO is our standard for aldehydes. So if you have 3 carbons, that's your core kind of fundamental group. That's the smallest you can get with a chiral atom. You can then move to 4 carbons. You now get 2 chiral atoms, and you get branches within the family tree. Right? Every single one of those has a core functional name. Right? So glucose is somewhere in there. Is that glucose? Anybody remember the structure? You think it's F? You can cheat.
No.
2, 2, 1, 2. I don't know why I'm calling it 2, 2, 1, 2. I think it's 2, 1, 2. So this is shown as the D. In fact, all of these are shown as the D carbohydrate. So there's another tree that looks exactly like this, except that penultimate carbon has it the other side. And if you look at biochem, theoretically you should be able to name all of those, but more than likely you wouldn't be responsible for that. What you'd be responsible for naming is the ones that are biologically relevant. Not all of them show up in biology. Okay? With that, we're at time.